Hi everyone. Today we're going to continue talking about motion in the sky. We're going to be looking specifically at the planets in our solar system specifically. So by the end of this lecture and this week, you will be able to recognize patterns in the motion of the planets, explain retrograde motion of both the inner and the outer planets, and also describe the Milankovitch cycles and how they affect the climate on Earth. So to start, the planets in our solar system are called planets because it comes from the Greek word for wanderer. So planets do not emit their own light. We're seeing their reflection of sunlight. So similarly to how we see the moon. The planets are not emitting their own light the way that stars do. We're just seeing the reflection of the sun. So the outer planets appear to move eastward in the sky. So the outer planets being the planets that are on the outside of Earth. So Mars, Jupiter, Saturn, Uranus, and Neptune. They are further away from the Earth than the sun. They're on the other side of the Earth from the sun. They are farther planets, so they are moving slower around the Earth. Around the sun. The inner planets, which we call Mercury and Venus, these are the planets inside of Earth, so in between Earth and the sun. They appear to move eastward, westward, and back again in our sky. Their orbits are inside of Earth's orbit. So you'll notice here is Earth. Oh, I lost my pointer. There we go. This is Earth with our moon whipping around. And you'll see Mercury and Venus are on the inside, also rotating around the sun. And then you'll see the other planets are on the outside of Earth, also rotating around the sun. You'll notice that the inner planets are moving faster, the outer planets are moving slower than Earth. So let's go into the patterns that these planets make on our sky. So this is our celestial sphere, if we flattened it out into a map. So the celestial equator is the thick white line in the middle. So the top part is the northern celestial sky, the bottom part is the southern celestial sky. So when things are in the northern half of this figure, that means that object is in the northern sky. So you'll notice the stars are stationary in the background. These, of course, are not all of the stars, but some of the main ones. And then we have the motion of these planets throughout the year. So first, let's take a look at the sun. So the sun is this orangey yellow symbol with a dot in the middle. The Earth would be the same symbol but with a plus sign in the middle, if you see that in the future. So the sun is the circle with the dot in the middle. So we've seen the path that the sun takes in this class before because we call that the ecliptic. So we know that the sun is going to be in the northern the northern celestial hemisphere in the northern hemisphere's summer. And then in the winter time, the sun is going to be in the southern sky, in the southern celestial hemisphere. So if we take a look at the planets now, you'll notice that Mercury is the yellow planet. You'll notice Venus is the blue planet. So these are the inner planets. So these are the planets closer to the sun than we are. And you'll notice that the location of these planets is never too far away from the sun. You'll also notice that the sun makes a nice smooth path, but the planets do not. So they do these loop-de-loops. There's a loop of Mercury. Here's going to be a loop of Venus. So they do these loops where they seem to move backwards for a time and then they catch up to their path again. They also move fairly quickly. Now, if we look at the outer planets, here we just have Mars, Jupiter, and Saturn. You'll notice Mars moves at an okay speed, almost keeps up. But Jupiter and Saturn are moving much slower. You'll notice, however, that they look like they're moving to the east, but they also have these pause and flip around, go backwards periods. So Mars does it over here. Oh, it's the next loop. Mars does this reverse, as well as Jupiter and Saturn. So Mars, Jupiter, and Saturn are moving a little bit slower, but you'll see that they do these reverse or these loops the same way that Mercury and Venus do. So the sun does not. But the planets, each of them, do have these loop-de-loops. So let's look first at Mercury and Venus. So Mercury and Venus stay near the ecliptic, as we saw in that GIF on the previous slide. They're never far away from the sun. So the only time you can really observe Mercury and Venus is when the sun has set or when the sun has not yet risen. So when the sun is out, you generally can't see the planets. It's too bright. So if Mercury and Venus are behind the sun in terms of their path, so to the west of the sun, you can wait for the sun to set, and then you'll see Mercury and Venus for a little while before they set. If Mercury and Venus are ahead of the sun in their path, if they're to the east of the sun, you'll be able to see them at sunrise. So right before the sun rises, you'll see the two planets rise before the sun. Once the sun is up, you will not be able to see the planets because it's too bright. So Mercury and Venus have smaller orbits than Earth, and they appear to be crossing back and forth across the sun. So as we saw in the video previously, it looks like Mercury and Venus are crisscrossing throughout their orbit. So they're crisscrossing, they're looping around the sun. So this loop is what we called retrograde motion. So I have a video that I think shows, a video that I found on YouTube that I think shows a couple of diagrams that really nicely explain retrograde motion and how it works for both the inner and the outer planets. So I will show you that right now. It is here. So it's going to go into both the inner and the outer planets and why they appear to make that loop-de-loop in our sky, which we call retrograde.
You may have heard that Mercury is retrograde again, but if you try to find out what that means, search results are dominated by astrologers who believe that Mercury can make you spill coffee on your favorite shirt or cause your car to break down. But if you set aside all of those creative interpretations, there's actually a real astronomical phenomenon underneath. So let's start with the basic layout of the solar system. The planets closest to the sun move faster and the outer planets move slower, but they all go in the same direction. Apparent retrograde motion is when the planets appear to temporarily change the direction of their orbit. They don't change direction, it just looks that way from Earth. It's an illusion that unfolds over a matter of weeks or months. In this image, Mars was photographed every 5 to 7 days between October 2011 and July 2012. Once all the photos were combined by aligning the stars in the background, it appears as though Mars looped back on itself before continuing on its orbit. A retrograde illusion like this happens when we lap an outer planet like we do with Mars every 2 years, or when an inner planet laps Earth like Mercury does every 4 months or so. But for both Mercury and Venus, the illusion is hard to actually capture, since they're located on Earth's day side, not on our night side. When those planets are visible, it's only right around sunset and sunrise. But assuming you could see it, here's a diagram of how the Mercury retrograde illusion would work. This line shows our view of Mercury against the background stars. As Mercury passes us by, our line of sight shifts so that for about 3 weeks, Mercury will appear to loop back on itself when viewed from Earth. It's simply a function of two objects orbiting in the same direction at different speeds. If you stood on Mercury, you would see Earth make an apparent loop too. I wanted to recreate this illusion on a tabletop, so I stuck a post-it note to the wall in the background to represent the fixed stars. I grabbed a ball of Play-Doh to be Mercury, and my phone camera represents Earth. I took 10 photos of them orbiting in the same direction with Mercury passing by Earth. If you simply view the images in sequence, you don't really see the loop, but remember that the illusion is relative to the background of fixed stars. So once you line up the images so that the post-it note star is fixed, the retrograde loop appears. Here's another visualization of the retrograde loop of Mars as Earth passes it. The bottom part shows the positions of the planets, and the top is the corresponding view of Mars from Earth. The key is to always remember that Earth is moving too. So retrograde motion was baffling to early
So that retrograde motion is due to the fact that our orbits are different. So when Earth laps a planet, or when an inner planet laps Earth, the effect that we see from Earth is that retrograde motion, or that backwards motion, that loop-de-loop. So it should be noted that Mercury in 2020 was in retrograde 3 times. So if you're trying to blame your clumsiness on Mercury being in retrograde, it's just a natural thing that happens as Mercury laps Earth around the sun. So Mercury and Venus are the inner planets. They are lapping Earth, causing us to see a loop-de-loop or a period of retrograde motion in their apparent paths. Remember that Mercury and Venus are always found near the sun. Now, the outer planets, their orbits are larger than ours. So similar, except just as the video said, it is as Earth passes by the outer planets that we appear to see this loop-de-loop. So here's a diagram showing Mars. So as Earth passes by Mars, what we end up seeing is a bit of a slowdown and then a reverse and then a speed back up. So the path of Mars also has this retrograde. Mercury, I mentioned, there were 3 different retrograde times in 2020. However, Mars is only in retrograde about once every 2 years. So here is another map of that retrograde loop that is formed. This is these are images and star maps from 2003, but shows a nice retrograde loop there. So now that we've thought about the path and the motion of all the other planets, let's think quickly about the motion of Earth. So we know that Earth rotates around its axis and it revolves around the sun. But that's not all. There are also 3 different cycles that we call the Milankovitch cycles that have a pretty big influence on Earth's climate. So astronomy actually has an influence on the climate that we have here on Earth. So these Milankovitch cycles are very long-term cycles, so they cause very long-term changes in climate. For example, ice ages. So these 3 Milankovitch cycles are eccentricity, which is the change in our orbit, tilt or obliquity, which is the change in the angle of our tilt, and then precession, which is what we talked about earlier. It's the change in where our pole is actually pointing. So let's get into them a little more. Eccentricity, this is how elliptical is our orbit. So our orbit around the sun actually changes. The cycle is about 100,000 years. So we go from a more elliptical orbit like this yellow one to a more circular orbit like the pink one. So it is not as extreme as this. This is a very dramatic diagram, so it's not as extreme, as shows in this diagram, but there is a slight change in the our elliptical orbit. So it goes a little more elliptical, a little less elliptical in about 100,000 years. And this is due to the interactions of the gravity of other planets. So we also have obliquity. So obliquity is the tilt of our axis. So this is a 41,000 year cycle. And currently, our axis is tilted at about 23.5 degrees to the vertical, but it actually varies. So it goes from 21 to 24.5 degrees, and then back every 41,000 years. So this is, again, due to the gravitational force between the other planets as well as the moon and the sun on Earth. So our angle of tilt actually shifts over time. The last of the Milankovitch cycles is called precession. So this we've talked about. This is about a 23,000 year cycle. And this is the fact that our axis wobbles. So Earth is not a perfect circle. So it wobbles like a top would when you spin it. Currently, right now, our North Pole and our North Celestial Pole point almost directly to Polaris, our North Star. But we know that over time, our north celestial pole will shift as our axis wobbles, and our North Star will change. We will have a different star directly to our north than Polaris. But remember, this is about a 23,000 year cycle. So these are all very, very, very long-term cycles. Very long-term, very slow changes. So these three factors really affect our climate on Earth in a very large way, but in a very slow way. So these cycles have a big influence on ice ages and the formation versus retreat of glaciers on our Earth. It's very complex, but very periodic. So we know these cycles, we know the timing of these cycles, so we know that the influence on Earth is going to follow that specific timing. So how do we know this? The cycles were actually proposed in the 1920s, but they were not validated or proved and accepted until the 70s. And it took sediment cores from the ocean that could actually determine the temperature back in time for anyone to believe or for this idea to be accepted as true. Because of course we know we need evidence to believe any science. So it took until the 1970s to get this evidence once we were able to drill these sediment cores and use the chemistry of the sediment cores to determine the temperature of Earth back in time. So we're able to match the temperature changes with the predicted changes in heating coming to the Earth from these Milankovitch cycles, and it matched very, very well. So it proved that the Milankovitch cycles are true, and they do have a big influence on our the input of solar heating that we get, and therefore the temperature on Earth. So I should note, I have said a couple times that it's a very long-term cycle. Please be aware that this is very, 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 very long-term, and these cycles are much too large to explain any of the current and recent climate change. So any climate change that is happening currently that you hear about, the Milankovitch cycles are much too slow of a scale for the Milankovitch cycles to be playing any role. So that has been completely ruled out as to our current climate change. So here we have a figure showing the path of planets. So here we are seeing two different retrograde motions. So here we have one planet, here we have another planet. So you can guess that this planet is moving much faster. It must be a planet closer than Saturn is, because this one is labeled Saturn. So we see that this planet moving faster, covering more space, must be closer than Saturn. So question, which of the planets do not appear to move backwards at any time along their orbit? It's a trick. All of the planets appear to move backwards at some time along their orbit. So both the inner and the outer planets appear to move backwards as the orbits pass each other. So Earth would also appear to move backwards from any of the other planets, because either that planet is lapping Earth or Earth is lapping that planet. So we're still going to have the retrograde effect. So Earth would also have periods of retrograde motion from any of the other planets. So why would it be hard to photograph the orbit and the motion of Mercury and Venus? So usually we see Mars, we see Saturn, we see really nice pictures like I've showed of their paths over time. Why might we not have photographs of the paths of Mercury or Venus? Take a second to think about that. If you're thinking, well, I know Mercury and Venus experience retrograde motion, but I also know Mercury and Venus are always near the sun, so they're never far from the ecliptic, you are absolutely right. So it's hard to photograph Mercury and Venus on their path, on their whole orbit, because they are always near the sun, so we can't always see them. We don't have a clear night to photograph the whole orbit of Mercury and Venus. So here again, you'll notice Mercury and Venus, the yellow and the blue, are always right near the sun, but you'll see that retrograde motion, that back and forth loop-de-loop. You'll notice that Mars, Jupiter, and Saturn do eventually veer far from the sun. They don't follow the sun as closely. They are also moving slower than the inner planets. And you'll see that the apparent path of all of the planets is actually from west to east. So throughout the night, they will move from east to west, just as everything does. But over the course of time, just like our sun, we will see that the planets actually move against the backdrop of that celestial sphere from west to east. So you'll notice that the planets are all following a similar path, west to east. They all have these periods of retrograde motion, and it's Mercury and Venus that are always right near the sun. They're never far from the ecliptic.